All right, so the next concept I want to talk about is heat and heat transfer. Um, what you have to remember is that heat really is a process, not a quantity that a substance has. Heat is what is energy that's transferred between two substances. Um, and usually in the context of thermal energy. We, we add heat to an object, this will change its internal energy and will change its temperature. It might change other properties of the material also. Okay. All right, so think about heat. We take an object that has some block of something that has a certain mass, and it has some temperature T. What I can do is add more energy to this material. Okay, so I can do this in various ways. I could add energy to it by throwing it through the air, right? Then I've added net kinetic energy to every atom in that object. Now, eventually, as I throw it in the air, it's going to run into air molecules. It's going to hit the ground. It's going to roll on the ground. And some of that energy that I've given it in kinetic energy will be converted into internal motions of atoms inside the block. And so that energy will be converted into these internal uh, degrees of freedom of the atoms within the block, okay, and turn into an increased temperature, okay. Um, so really, it depends on how I add the energy. But we're going to be concerned with here is energy that we add that finds its way, okay, to changing the internal energy of the system, changing the random vibrations, changing the energy stored in the potential energy and the spring forces, the effective spring forces between the atoms inside, okay. And there's various ways to do this. So, one way to think about heating an object. I mean, you guys have all heated objects before. Um, you can, for instance, put it on your stove. So what you do when you do that, you take a pot of water and set it on the stove, and you heat up the filament, or maybe you put flame under it. You're really putting it in contact with another object that's hotter than it is. Okay, so I can take my block here and put it in contact with another block that has a higher temperature. T2 bigger than T, okay? And what will happen is that energy will be transferred between these two. And the way that happens physically is that the atoms in the block number 2, let's call this T1 and T2, block number 2, because T2 is hotter, they're vibrating around with larger average kinetic energy. Okay, and so at the interface between these two here, there's going to be a connection, a contact between these different populations. In block 1, the atoms are kind of moving sluggishly. In block 2, they're whipping around in there. And again, when I say whipping around, of course, you take a hot object and put it in your hand. You don't necessarily see that the edges of the object are being distorted by large motions of material. It's really, it's a very low level vibration that you can't perceive aside from the sensation that it's hot. Okay, but I put this block next to the block 1, and the vibrations of the atoms in block 2 will transfer energy to block 1 via collisions, for example, between the particles. You'll give up some of the energy that the particles at the interface have to T1. And this will continue until the heat will flow, energy will flow from one block into the other until the temperatures are equal. And then at that point, the average energy in each particle in block 1 is the same as the average energy of each particle in block 2. So when they collide, there's not a net transfer of energy. There's going to be exchanges of energy backwards and forwards, but on average, you're going to have a zero flow of energy from one block to the other in the form of this random energy. Okay. Now, so you've envisioned this process by which the two blocks equilibrate. They come to the same temperature. Now, note the temperature in the end is not going to necessarily be T2 or T1. It should probably be in between, because you're going to take energy out of the second block and deliver it to the first block. And so the average energy internally to block 2 is going to go down because I had to give some up to heat up block 1, and so the two blocks are going to come to some temperature that's in between. And so we want to find out a way to characterize that. And the usual way to do it is to say that If I'm going to change the temperature of an object, it takes a certain amount of heat. I have to inject heat into the energy, the internal energy of the random vibration, and the internal energy of the the spring forces or the effective spring forces. Or for I mean, I didn't mention this in the last video, but there are other degrees of freedom I can consider aside from spring forces and motion. I can consider rotation. Okay, so if I have molecules in a gas, they can rotate, they can vibrate if they're diatomic. They act like little spring mass systems on their own, okay, and they can vibrate and rotate. So you can store energy in all these things, okay. So it takes energy to get well, basically you're increasing the average amount of energy in each one of those types of motions of each atom, okay. So it takes some energy. So the way that we consider that energy, we talk about the heat that's required to be transferred, and we use Q for that. So that's an amount of energy that has been given to the object, will be proportional to the change in the temperature of the object. Okay, and the usual way we write that proportionality is it's going to be proportional to the amount of stuff, because for every atom I have to give that atom enough energy to match the temperature of the object. So the more atoms there are, the more energy I have to give the object to get its temperature up. So we write it as being proportional to the total mass of the object, m. And then we have another constant proportionality, which is called the heat capacity, C. So the heat capacity is the fudge factor where we hide all the physics, okay? And often the fudge factor is measured. So we'll measure, the heat capacity of a solid, okay? In some cases, you can calculate it. It turns out we can calculate it for ideal gases, and we'll show that in Chapter 18. Okay, or is it beyond that? No, it isn't 18, right? Okay, so this tells me how much heat is required to change the temperature of an object, and this is some intrinsic, some coefficient that tells us the constant proportionality, and hidden in here. So this is the total amount of stuff I'm heating. Hidden within the C is the information about where within this object I can stash energy. Okay, so again, it's on a per atom kind of basis because I'm counting up the number of atoms here in this term. But for each atom in the material, how can I store energy? And again, that can be motion, it can be rotation, vibration, potential energy in the stretch of springs. All these things can be places where you store energy. And again, the fundamental concept about temperature is that if an object has a certain temperature T, that tells me that every single one of those possibilities has average energy 1/2 kT for each atom. So I've given each possible degree of freedom, each possible way to store energy has 1/2 kT of energy. Okay, and so for a simple gas, the heat capacity, if it's just a monatomic gas, the only place you can store energy is in the motion, the linear motion of the gas atom. The heat capacity will be less than it will be for a solid where there's more degrees of freedom in the system. Okay, and so it takes less heat to raise the temperature of a gas than it might to raise the temperature of a more complicated material like a solid. Now, I have to be careful there. I mean, that's a very generic statement, but the idea is that the heat capacity reflects how many places you can store energy. And for every one of those places, you have to give it 1/2 kT if the material will have temperature T. Okay. So that's what C accounts for. And so if I now go back to this problem where I've got these two objects in contact and I'm going to let them equilibrate, a certain amount of energy is going to be transferred, okay, out of block 2 and into block 1, because block 2 is the hotter one. And so that amount of energy will be the same going from one way versus the other. So if I say how much heat flows into block 1, that's equal to the heat that leaves block 2. So the way I can write that is the heat that flows into block 1 will be M1C1, and then the temperature change for block 1. And that has to be equal to and opposite of, but what I'll do is I'll switch the sign on the temperature of the heat that flows out of block 2. Okay, oops. Let me Okay, and this will be delta T2. Now the idea is that delta T2 will be negative to account for the minus sign that I should be writing here, because the direction of heat flow does matter. The energy is lost from block 2 and gained by block 1. Now the temperature change, so in the end, the temperature of the two blocks is going to be equal. Okay, so we know the final temperature of both. So we can write this as M1 C1 is, oops, sorry. You know what, let me leave the minus sign here just to make it clear, because the heat gained by one is equal to the heat lost by the other one, so the minus sign there is to account for that. And this will be the final temperature. I'll do TF of the system minus T1, and this is going to be minus M2 times C2. See if I have room here. T final minus the initial for 2. Okay? All right, so that's now the equation I have to solve. And the amount of temperature change of one object versus the other is dependent on the mass of the objects and the relative size of the objects, and then, you know, how they store energy, right? So if C2 is a gas and 2 is a gas and 1 is a solid, for example, I might have to change the temperature of the gas significantly to increase the temperature of the solid. So for the same amount of heat, I get less temperature change. And so, you know, it's unclear until I tell you of something more about the masses and the number of atoms, which is reflected in the mass, and the heat capacity, where the temperature is going to end up. But you know it's going to be somewhere in between of these two objects. Okay. All right, a couple more concepts, and then I'll stop this video. So when you add heat to an object, you can do more than change its temperature, okay? So when I heat objects up, they change their shape, they can change their phase of matter, okay? And these kind of things take energy. So if, for example, I heat up a balloon that's full of air, okay, and I add some heat into it, the balloon's going to expand. So you're going to actually use some of the energy that's in this heat that I'm putting in to blow the balloon up. Okay, and so that energy is used at the expense of increasing the temperature directly. So the temperature goes up at the same time too, but I'm also using energy to change the density of the gas. So I'm expanding it. And in general, materials can change form, change shape as I heat them. So you take a solid piece of metal and you heat it up, it will tend to expand. Okay, and so you have to consider that also, and that's that process will use some of the energy, and the temperature change will be a little bit less because I've now changed the volume of the material. And so, as we'll see when we talk about gases, you'll have a specific heat associated with a gas that's at constant volume. So in other words, I don't allow it to expand. Okay, then more of the energy will go into changing the temperature because I'm not letting it change its shape. And you'll also have a specific heat at constant pressure, which is when okay, now I let it expand against a background gas. That's the balloon case. If I have a gas in a balloon and I put heat into it, it's going to expand. And it's going to expand so that the pressure in the balloon stays the same as the pressure outside. That's how you maintain equilibrium across the membrane of the balloon. And so there'll be a different coefficient, specific heat coefficient for that process, because the way the energy is used is different. I have to expand the balloon in addition to changing the internal energy of the object. Okay. All right. So, all right, just to keep that in mind, that objects will deform and expand because of heating, and that is considered separately, potentially, from the change in the internal energy of the system. I have to expend some energy to do that. All right, now the last thing is phase changes. Okay, so if I, take a block of ice and I set it out on the counter, eventually it will melt. Okay, and the reason it melts is because it's being heated up. It's trying to obtain the same temperature as its surroundings. Okay, so if I take an object and put it in a hot room, it's going to eventually take your drink out of the fridge and put it on the counter. If you wait long enough, heat will be transferred from the air in the room into the can of whatever, and it will obtain the same temperature eventually after a long time. So if I put a block of ice, it's trying to reach the same temperature as the outside world, and in the process it changes from a solid to a liquid. Okay. And so that energy that goes into converting it from a solid to a liquid, which means converting it from a system where the interactions between the particles, the spring forces, are strong and can basically constrain the atoms in a lattice that acts like a solid. But if I give too much energy to the atoms by heating them up, those springs get broken effectively. And so a solid to liquid transition is effectively breaking the springs that are holding the solid together. And it takes energy to do that. And it turns out that when you're doing that, you don't change the temperature of the object. So an ice cube will melt at 0 degrees at its melting point, and stay at that temperature until all of the ice is converted over into water. So the energy that you put in to an ice cube at the melting point will entirely go into breaking the springs, and no additional energy will go into changing the temperature until you've converted all the so in that case, the heat that goes in is not proportional to the temperature change. Instead, what happens is you get heat that gets used up in converting solid into liquid. Okay, and this is so basically, as you melt something, you're going to take a certain amount of energy to complete the melting process, and then once you've melted it completely, now the temperature can start to go up again, because now as you put energy in, instead of going into breaking springs, it goes into the other internal degrees of freedom. Okay. And of course, the same is true if I'm taking a liquid and turning it into a gas. There's a phase transition that occurs where the temperature is held fixed at 100 degrees C, and I just put energy in, and every bit of energy I put in will convert an atom that's trapped in the liquid into a free gas molecule that will then boil off the top. Okay, and that will continue. So this is why when you boil water to cook something, you can't raise the temperature above 100 degrees. The water will just boil. It's not going to get any hotter. Okay, so the hottest you can make your water is when it is the transition point between liquid and gas. Now there are ways to make superheated water by using tricks and pressurizing it and things like that. But the water on your stove will, once it boils, that's as hot as it's going to get until you've evaporated and turned it all into steam. Then you can heat the steam beyond that point. All right, maybe that's enough said about this. I'll stop here.